This is the continuation of our lecture in hydrostatics. So we discuss now the pressure head. Pressure head is just the ratio of the pressure and the unit weight of the fluid. It came from our general formula for determining the pressure, which is equals to the unit weight of that fluid multiplied by the height. So the equivalent height of the fluid needed to obtain that pressure is your pressure head. So if we want to convert pressure head between different liquids, say we have liquid A to equivalent pressure head to liquid B, so here are the corresponding solution. So as you can observe from the three solutions that we have, we only need to multiply the given pressure head of liquid A to the ratio of its corresponding fluid properties between liquid A and liquid B. The first one is we take the ratio of the specific gravities of liquid A and the specific gravity of B. The second one is we multiply the pressure head of A to the ratio of its mass density to the mass density of liquid B. The third one is we can also use the unit weights or the ratio of the unit weights of A and B. So depending on the given values, if we want to convert a pressure head between two liquids, we can use either of these three equations. So the next one is if we want to convert the pressure head of any liquid to equivalent pressure head of water, so we can just simply multiply the specific gravity of that particular liquid to the height of that liquid. So the solution just came from the solution because if we want to convert the pressure head of any liquid to pressure head of water, which is here on HB, so it means that the specific gravity of water on B is 1. So if the specific gravity of water is 1, so we can just simply multiply the specific gravity of that liquid to its height. So if we want to convert the pressure head of any liquid to to water, just multiply the specific gravity of the liquid and its pressure head or its height. Okay, for pressure measurement, here are the instruments used in measuring gauge pressures. So the first one is we have piezometer. It is the simplest form of manometer, which is tapped into the wall of pressure conduit for the purpose of measuring the pressure. So we just uh, put the piezometer there and we determine the pressure head of that fluid, and through that pressure head we can now measure the gauge pressure that is within that conduit. The next one is manometer. Manometer is simple and expensive device of measuring pressure and pressure difference. Open manometer is a tube bent into U-shape to contain one or more fluid of different specific gravities. So this is an example of an open manometer. And we have a differential manometer. So it cannot measure pressure, but it can only measure the pressure difference between two fluids. So frequently in hydraulic problems, a difference in pressure is more useful information than the pressure itself. So given that we have two conduits here, differential manometer can be used in measuring the pressure difference between these 2 points. So this is the general equation for the pressure difference. This general equation is applicable for open manometer and uh, differential manometer. So P2 is equals to P1 plus sum of product of unit weight of fluid times H down minus sum of product of unit weight of the fluid times its corresponding height up, or we can rewrite it as the pressure difference, which is P2 minus P1, is equals to plus the sum of products of unit weight times its corresponding height minus sum of the product of unit weight times h for up. So we have a sign convention here that all down are positive and up is negative. So what does downward and upward means? So how do you identify the product of unit weight and its corresponding pressure head, which is going downward? So let's say we have here the open manometer. So let's say fluid 1, the starting point or the location for pressure 1 is at this point. And the location of pressure 2 is the end point of the fluid, which is this one, P2. So we have P1 and P2. So these are the location of your starting point and end point. So it means our direction from the starting point going to the end point goes in this direction. So we have two fluids here. So if we can rewrite P2 is equals to P1, or we can use also this P2 minus P1. P2 minus P1 is equals to sum of product of unit weight of H. So uh, focusing on the manometer, we have two fluids here. Um, Considering fluid 1, our starting point of fluid 1 is at P1 and ends or at the centroid of this conduit or this pipe, and it ends at this point. Okay, so that's the end point of that fluid 1. So measuring the difference in elevation or the vertical distance between the two, that's your corresponding H for that particular fluid. Let's say this is your H1. So from starting point to end point of that fluid, so the starting point is lower than the end point. The end point is higher than the start point, so it goes up. So it goes up. So we will use negative sign for upward direction. So we have negative product of the unit weight of fluid 1 multiplied by its corresponding difference in elevation or its pressure head, which is H1. Next, fluid number 2, color blue. So color blue starts here and ends there. Okay, measure its difference in elevation. That's your pressure head H2. So it has a unit weight gamma 2. So starting point is going upward. It starts here and end above. So it's upward direction. So it means we use negative. So minus gamma 2 H2. So if we have given P1, or depending on the problem, we can now solve the solution on this open manometer using the general equation that we have here. Okay, and so you solve this. How about this differential manometer here? Let's say we can start here as your point 1 starting point and end at the fluid number 2, um, P2. Okay. So you can also interchange the starting point of your solution. You can start here at fluid 2. Let's say in this solution we start at fluid 1 where P1 is located and fluid 2 is the endpoint where P2 is located. So this is your start. This is the end. So the direction from here P1 going to P2. Okay. So again, pressure difference is equals to okay, considering first fluid 1, let's started here and ended there. So their difference in elevation is that the starting point is lower than the end point of fluid 1. So it is going up from start to end, going up. This is H1. We have unit weight 1. So we have the first one, sum. This is going upward, so that's negative. Going upward, negative. Product of um, unit weight of fluid 1 and H1. Next, fluid number 3. Fluid number 3 started here and ended there. So going up again. It's going up. This is say H3. So unit weight of fluid 3. So the product of unit weight and its height. So it means uh, going upward is negative. Negative H3. And the last is fluid number 2. Started here ended at the location of P2. So the difference in elevation is this one, say H2. So H2 starting point and point is slower, so it's going downward. So started here and there H2, so positive unit weight 2 H2. Okay, again fluid number 1, it's going upward, difference in elevation. So the starting point is lower than the end point, so we have a negative sign. Then for the fluid number 2, the starting point of fluid number 2 is lower than the end point of fluid number 3 rather. The starting point of fluid number 3 is lower than the end point of fluid number 3. So that's still going upward, which is negative. Then fluid number 2 is uh, has a starting point that is higher than the end point of the fluid in terms of its uh, difference in elevation between the points. So fluid number 2 has a positive sign for the product of unit weight and its corresponding height. So this is the solution for that figure. Right. So let's solve some problems. Okay. Question number 1. The pressure on a closed tank reads 60 kilopascal. What is the equivalent height in water? What is the equivalent height of oil having a specific gravity of 0.8? What is the equivalent height in mercury having a specific gravity of 13.6? So the pressure head is equals to the pressure divided by the unit weight of the liquid. So if we have a given pressure of 60 kilopascal, if we are to determine the equivalent height in water, so say for water, let's just use the unit weight of water, which is 9.81 kilonewtons per cubic meter. So kilopascal is in kilonewtons per square meter, so that will be cancelled out, and what unit remains is in meter. So let's compute that. We have 60 over 9.81. Sorry, that's 60 divided by 9.81. 6.116 meters. For letter B, the equivalent height of oil, or the pressure head for oil. So using the same solution, we have the pressure, and it is divided by the unit weight of the fluid, which is oil. So to determine the unit weight of oil, if we have a given specific gravity, the unit weight of any fluid is equals to unit weight of water multiplied by its specific gravity. So we can rewrite this as unit weight of water times the specific gravity of oil. Okay, so we have a pressure of 60 kilopascal to be divided by 9.81 kilonewtons per meter, unit weight of water, times specific gravity of 0.8. 60 over 9.81 times 0.8. So that's 7.645. 645 meters of oil. Letter C. We have mercury with a specific gravity of 13.6. H equals to P over unit weight of mercury, Hg. So pressure over unit weight of water multiplied by specific gravity of mercury. So we have here 60 kilopascal over 9.81 kilonewtons per cubic meter times 13.6. So I'll just change this to 13.6. So the height, the pressure head for mercury is just 0.4497 or 0.45 meters. Okay, so given pressure of 60 kilopascal, uh, these are the equivalent pressure head for water, oil, and mercury. Okay. Next, problem number 2. Pressure in a given tank reads 290 mm of mercury. Specific gravity of mercury is 13.6. Determine the equivalent height of column of water. Determine the equivalent height of column of kerosene, and determine the equivalent height of column of nectar, which is 2.94. So let's solve this. So the pressure reading here is 290 mm of mercury. So it means that we have a pressure head of mercury, which is equals to 290 mm. or in meters divided by 1000, we have 0.29 meters of pressure head on the top. So another, we have specific gravity of 13.6. Specific gravity of Mercury. The first required is to determine the equivalent height of column of water. So the solutions here, we have three solutions from the discussion earlier. The solutions are, if we are to convert the pressure head of liquid A to liquid B. So we use the ratio of its specific gravity, or we can use the ratio of mass density and unit weight. Okay, so based on the given, we have specific gravities given. So we will use the first solution. But since on the first question, we are required to determine the height of column of water or the pressure head for water, so we can just simply multiply the specific gravity of the liquid, and its height. So the liquid given is mercury. So the specific gravity of mercury multiplied by the height or the pressure head equivalent of mercury. So specific gravity is 13.6 for mercury multiplied by pressure head of 290 mm or 0.29 meters. So 13.6 times 0.29. It's 3.944. 3.944 meters. Okay, that's the answer for A. For B, convert it to kerosene. Specific gravity of 0.82. So specific gravity S for kerosene is 0.82. So same procedure. Uh, since it's not water, we can use now this solution right here. So the height for the kerosene is equals to specific gravity of A, which is mercury, over specific gravity of kerosene multiplied by pressure head of mercury. So substitute now. Specific gravity of mercury 13.6 divided by 0.82 times 0.29 meters. So we have here 13.6 over 0.82 times 0.29. So the answer is 4.8097 or 4.81 meters. That's your equivalent pressure head for kerosene. For letter C, equivalent height of column of nectar. So for letter C, nectar is 2.94. That's the specific gravity. So the height of pressure head for nectar is equals to specific gravity of mercury over specific gravity of nectar multiplied by pressure head of mercury. So this equals to 13.6 over 2.94 times 0.29. That is equals to, let's just change the specific gravity which is 2.94. So the answer is 1.341. 1.341 meters. So that's the answer. Okay, next question. Number 3. What is the equivalent height in meters of water gauge for an absolute pressure of 6 atmosphere when the barometer reads 760 mm of mercury? Unit weight of water is 9.79 kilonewtons per cubic meter. Also compute the gauge pressure. So we are required to calculate the gauge pressure. So if we have here a given absolute pressure, just recall the solution in determining the absolute pressure, which is equals to the pressure gauge added by the atmospheric pressure. So here we already have given absolute pressure, which is 6 atmosphere. Also the atmospheric pressure, because the barometer is used for measuring the atmospheric pressure, so it means the reading on the barometer is your atmospheric pressure. So we have 760 mm of mercury. So actually atmospheric pressure is expressed in mmHg. It means that we have a pressure head of 760 mm of mercury, but they also use this as the unit of pressure. So for us to have consistency of unit, um, we convert this to Pascal. So uh, we can try converting atmosphere to Pascal using our calculators. But if you already know the conversion factors, then that's good. But if you don't know the conversion factors, we can use our calculators. If you are using Casio calculators, just click Shift, Convert, Shift 8. So if you're using Casio FX570 or 991ES, so here in my virtual calculator, just look for the unit that we are going to convert. So in your calculators in Casio, that's number 20, number 25. Okay, number 25. Shift 8, Shift Convert, and press input number 25 to convert atmosphere to Pascal. So the pressure uh, from atmosphere to Pascal. Okay, so just input the value. Okay, it means 6 atmosphere is equivalent to 6,000 607,950 Pascal. Okay, for atmosphere, for mmHg or mm of mercury to Pascal, in your calculators for Casio 991ES or 570ES plus, press Shift, Convert again, and select or input number 27. Okay, number 27 there is mmHg to Pascal. Okay, so means that here in my calculator, I will just search for mmHg, millimeter of mercury to Pascal. So I will just directly input 760. Okay, 760 here. So that's 101,325.024 Pascal. Okay, so that's it. We can now substitute the absolute pressure and atmospheric pressure so that we can determine the gauge pressure. So the gauge pressure is equals to absolute pressure minus atmospheric pressure. Okay, so absolute pressure is 607,950 minus 101,325.024 in Pascal. So subtract 607 950 101 325.024 500 506,624.976 Pascal. Or if we convert this to kilopascal, just divide 1000. 6.625 kilopascal. So we already have the answer for question number 2, which is to compute the gauge pressure. Now, what is required is to determine the equivalent height in meters of water in the pressure gauge. Okay, so we already have the gauge pressure, which is 506.625 kilopascal. So to determine the height of water, okay, going back to our general formula for determining the pressure head of any fluid, we have pressure over the unit weight of that particular fluid. So pressure is 506.625 kilopascal or kilonewtons per square meter to be divided by the unit weight of water. So the unit weight of water that is given here on this problem is 9.79 kilonewtons per cubic meter. So we will use that 9.79 kilonewtons per cubic meters. So divide the two. 506.625 divided by 9.79. That's 51.749. Okay, so that's in meters. That's the height of water. Okay, so or this is the pressure head required to obtain this pressure right here, gauge pressure, which is 506.625 kilopascal. So that ends the second part of our lecture for hydrostatics.